Hello, my name is Deependra Soni, and from Pool 1, we have selected the paper tagging English text with a probabilistic model HMM. My teammates are Akash, Anurag, and Subham. So, the first topic comes in the paper, that is, what's the problem of pause tagging? What is pause tagging? What is pause? Pause means parts of speech tagging. Parts of speech tagging means if there is an English sentence, in English there is grammar. So there is parts of speech and each word is a part of speech. Either it is a noun, pronoun, verb, adverb, and one of the part from parts of speech. So a sentence is a sequence of words. If we have provided tag, pause tag, then uh, we need a same length sequence, that is W. The pair word and tag like this. The determinant dog noun is a alignment, and the procedure in which a sentence or a word is provided a tag is called tagging procedure. So there are two algorithms for tagging. The first one is rule based algorithm and the second one is probabilistic algorithm. So the first one is rule based algorithm. What is this? So in this, what is done, the rules are decided by some experts or linguists. Like rules like after a pronoun, that are general's rule. Like after a pronoun, usually a verb. After a possessive pronoun, noun. Sentence structures, almost there are too many sentence structure, but I have shown you previously a sentence. For that, the sentence structure was subject, then verb, then object. List of possible tags for each words. Like there is a word book. It may be noun or a verb. Like I am booking my ticket. Here book is a verb. And please give me an LU book. That is noun. Similarly, running. Running is good for health. Here running is a noun. I am running 5 kilometers per day. Here running is a verb. Some rules are also called morphological rules, like words ending in ing, uh, usually verb. Running, here running is a verb. If I'm taking some words which are ending with ly, like quickly, that is adverb. So these types of rules are decided with the help of some expert or language. So this is called rule based approach. This is a good approach, but this also contains some disadvantage or advantage type things. Like this is easy to interpret, language meaningful, but it is a uh, work on control language. It is a uncontrolled language. If you see some new words, the procedure is not helpful. This is very time consuming. So these are the disadvantage of this algorithm. Now the second one is probabilistic model for pause tagging. The meaning of probabilistic methods. In this, we provide probability for each sentence, each tagging sequence, and which tagging sequence got maximum probability, we give that sequence to the sentence. So in this, there are two important terms. The terms are transitional probability and emission probability. I will introduce these terms after some slides. So for the probabilistic model, there is an example like the dog runs. So I have taken only two tags. You also can consider more tags, but I have considered two tags like determinant, noun, and verb. Determinant, verb, and noun. If I have taken both the probability table, then I provide the value of emission and the sequences. So which model choose the sequence which with the high probability. Which one gets high probability? That is the correct one. So we have provided the tag for the sequence or the word. Now how will we measure that is it correct or not? Is it good or not? So there are two types of measuring tagging quality. Like the first one is sentence level accuracy. We check is the sentence is fully correctly tagged or not. If I have 10 sentence and I apply some procedure, using that procedure I found there are 5 sentences which are correctly tagged. So the accuracy for that one is 50%. Similarly, word level accuracy. In this, we check is each word is provided a correct tag or not. Like there is a sentence, the dog eats food. We give this determinant noun, noun, noun. So I found that this one is incorrect. There are 4 words and out of 4 words, 3 are correct. So the accuracy is 75%. Before some time, I said to you that I will introduce the emission and transitional probability after some time. So the meaning of emission probability is probability that tag T generates word W, like probability of uh, noun being dog. Like we have a noun. Now, what is the probability that the word is dog? The transitional probability is probability that tag T I follow the previous tags. Like after determinant, noun, and some other words, the verb is coming. How often does a verb follow determinant then noun? So there are two tagging procedure, two tagging algorithms. The first one is Viterbi algorithm. Second one is algorithm. We also have given we tag sequence for the whole sentence using dynamical programming. And algorithm, we are not providing tags in this. So we take each position I, pick the tag T that is most probable across all possible sequence. Now the best deserving model, the tri-class model is. Since this model works on fully joint probability theorem, this is the fully joint probability theorem. The first one is transition and the second one is emission. Replace two terms in the sequence. We replace both the terms using assumption. The first one is current tag depends only on previous 2 tags. The second one is emission, that is current one depends only its on tag. Just a second, I need to check is it recording or it. Find this replace terms and our tri-class model is ready. Now, number of total training parameters in the tri-class model. Vocabulary size NW, total number of tags NT. So possible value of H probability, total NT cross NT cross NT, total number of key probability NW cross NT, are summation of this value should be 1. Image 2, 1. So we minus 1 parameter 4. Let us understand this thing with one example. Suppose we have too many sentences and we select one sentence. For this one sentence, there are too many text sequence and I have selected this text sequence. Okay. So for step 1, I will calculate. We have given the word is determinant and what's the probability that the word is the into transition for word the. The first word after start, it is coming determinant. We have given noun and what's the probability that the noun is given, the noun is a word that is dog. Similarly for all, and then we found the complete probability for this sequence is multiplication of all. So we are training the tri-class model, our tri-class model. So there are two methods for training of tri-class model. The first one is relative frequency training and the second one is maximum likelihood training. So the first one is there are some new unseen terms. I will introduce these terms in the next slide. So relative frequency training and T1, T2, T3 is number of times text sequence this one this sequence appear and T1, T2 number of times tag bigram T1, T2 appears and WT number of times word W appears with tag T and N of T total count of tag T in the corpus. These are the transition and emission probability which I have shown you earlier. So in this there is a problem. Like we train our model and in our model we never train a sequence and such a sequence comes in test. So in test our href value will be 0. Like there is a sequence noun for tag noun. We train our model for some small sentence like 5 to 6 word, but in the training we found a sentence which contains a sentence of the length of 10 and in that sentence there is coming a noun. Since we have selected the correct text sequence for that big sentence, but there is noun this sequence in that sequence. Since our model have never seen this noun for the previous for the training part, so what this relative frequency model will do, it will provide correctly tagged sentence probability value that is 0. If it will provide 0, select that sentence. This is a very bad problem for 0 probability model. Like we are understanding with one example. These are our training data. So we count total. Then we compute these probability for the sentence, for the text probability. Like we have taken a dog eats food. We have to count. We have to use this formula. Calculate the value. The multiply 0, 1, 1. If we consider some other tags and calculate the value of the probability, then either we will get some lesser value or higher value. If we are getting higher value, then that sequence is correct. If we are then another sequence is wrong, since it is since that is having less probability. So I have discussed this problem earlier. So what's the solution for that? Solution for that is the value of h and k never become zero. How it would be possible if we introduce some new terms like h uniform and k uniform. So what's the h uniform and k uniform? Anti where anti number of text and k uniform number of here term that is beside lambda the using method. Handout data method is a method in which we try different lambda value and which lambda is performing perfect, good, best. We will select those lambda. The second one is maximum likelihood training. So this is a type of unsupervised learning. So we found the probability value with the help of previously discussed formula, and the objective of that formula is to then we will multiply all the sequence and found the maximum value, all the tagging sequence and found the maximum value. Which one have maximum value, we will provide that sequence. Like we will compute tag for each word of a sentence and which would give us maximum, which tag sequence uh, give us maximum, we will choose that tagging sequence. So in maximum likelihood training, we assume tags are hidden and try to find model parameters that maximize the probability of the observed sequence. This is example. We have some training data. Consider possible tags. This is sentence. We have selected this sentence and these are the possible tags. We can consider more tags, but we have considered only two. Then we count. We can introduce some initial probability, then use count probability value using formula, update emission probability, and repeat this procedure using forward backward algorithm and repeat until convergence. So I have named the forward backward algorithm two times. So what is this? This is a two-step algorithm. In the first step, that is called forward pass, we calculate probability of observing sequence up to position t. And in the backward, and probability of remaining sequence. Then this is the forward backward algorithm, a type of algorithm which see previous and upcoming part, both part. Now we have studied all the algorithms. Now it's time to discuss the experimental setup. In the paper, it is discussed that the data is selected tree-bank dataset, which contains 42,186 sequence, which are approx 1 million words. There are 159 tags and that are projected to 76 distinct post tags. We have taken 2000 text sentence, and our experiment is performed in these 5 different model. In the fifth one, there are 2 types of constraint. The first one is RF training. In the RF training, what is done? We use RF model, relative frequency model, and use different training sentence. In the first one, uniform, that is, we have taken zero sentence. We have not taken any sentence, and we found that the correct tags are 77. So why this is happening? This is happening because there are almost 50% words which uh, which took only one tag as a correct one, like the. What are the possible tags for the? Only one, determinant, right? So all the will get always determinant. That is correct. Some words are such words which take tags as correct only two. If I randomly select and provide, I can get 50%. So this is happening in this. So we are getting 77. And if I increase this to 40,000, get 97.0 best related. So the detail which I have tell, this is the graph. ML training from uniform distribution. The setup is first of all, ML training is a unsupervised learning, so there are no tags, so not no tagged data. Then we start with uniform probability, forward backward, then run multiple iterations. We are checking error rate, iteration, forward backward. We are also versus forward backward iterations. And that's error iterations are increasing, error rate is decreasing. Similarly, iterations was less, the perplexity rate was high, and it is reducing in a continuous way. These are the results. These are the same thing which I have told. The second experiment is ML on RF model. We have selected some RF model and then apply ML on those RF models. So the first one was 77% accurate, second one 95%, and similarly 7% accurate. Then I applied, then in the paper, performing on each of RF previously trained models, and we found that for the less trained RF model, our ML model is doing good performance. Like in the first iteration, it is become some better, in second some better, and increasing this betterness, and till 10th iteration it is reaching 86.86 from 77. So this is a good. From 90% good model, trained model, this was 92, 92.6. But when we use higher trained RF model, we are getting that our accuracy is not being increased. This is decreasing, and this is happening for all the higher trained model. This is same thing I have written there. This is the graph for all, like how it is performing, what's the error rate, and how it is uh, in decreasing with FP iterations. The fourth one is Viterbi versus ML technique. So in RF training, this is the initial. In RF training, we have used Viterbi and ML, both algorithm. Viterbi got this much accuracy, and ML got this one accuracy. This was the error, Viterbi error. This was the ML error. So we found the difference in error: plus 3 words, minus 3 words, plus 3, plus 16, minus 1, plus 12, 14, plus 8, like this. So what's the observation from this? Like this is a very little number, plus 3, minus 3, 16, minus 1. This is a very little number. So overall, the conclusion for this is choice of tagging procedure, Biterbi or Algo, ML, is not the critical factor. The turning point is means what matters is quality and quantity of the training data, not the tagging algorithm. The fifth one is standard ML versus TW constraint. TW constraint means we have keep P T given W fixed for 1000 most frequent words during every FB iterations. And what is the reason for this? Frequent word already have reliable RF estimates, relative frequency estimates. So this is doing some good thing like ML standard ML error 1365, TW constraint error 1365, same level. But as iterations is being increased, TW constraint ML errors also increase, but with not accuracy as the ML error. Like in the first iteration, it is 50 fewer, then 120 fewer, then 156 fewer, then 198 fewer. In the similar, when we reach at 10th iteration, it was almost 400 fewer. So this is a good thing. Error is still increase with iteration, but increase in slower than ML, right? So this is doing some good thing. The second one is standard ML versus constraint ML training. T constraint means this keep marginal tag distribution PT constant throughout the ML training. Okay, so this was standard ML and this was the standard ML results. This was TCML and this was TCML error. And this was standard ML error. If we compare, we start with same start and this is being lesser fewer with comparison with previous. In the 10th, that was 399, almost 400, and this is 55 fewer. So previous was better. So these are the results which I have discussed. Like T constraint help fewer error than standard ML, but still degrade the RF baseline 96.87. Improve over standard ML is small, over 16 to 55 fewer error. RF wins. Previously, algorithm wins. T constraint is harder to implement and tested only on bi-class model. This is a very good point. Since the uh, implement of this T constraint algorithm is something tough, so we use this algorithm. We means in the paper this algorithm is used only for bi-class model, not for tri-class model. So bi-class model, diagram formula, this one compare with tri-class model. Okay, these are the combined results for all the model which I have discussed. This is the good one. RF means relative frequency model for all training data. Starting the first model, 97.0%, and in ML, this one is better, ML4 and all data points with the 10 iterations like RF training, ML training, and best RF best. This is the same which I have discussed. And these are the conclusion points. The first conclusion is RF with higher tagged data give best result. Same one. ML training improve perplexity but not necessarily accuracy. The third one is ML training is only useful when label data is scarce. The fourth one is Bitterly and ML tagging gives nearly identical results. So the quality of data matters, not the algorithm. Model parameters count grow linearly in vocabulary size. Accuracy, which I have discussed, number of parameter for tri-class model, which I have earlier discussed, right? And these are the reference which I have used. Thank you.
Good morning. Myself Akash Kashyap, and today we are presenting the paper Efficient Estimation of Word Representation in Vector Space. This paper is introduced Word2Vec, which fundamentally changed how machine understand language. Instead of treating words as symbols, it represents them as vector that encode meaning. Now let's move to the introduction and background. Now let's begin with the core problem in traditional NLP. Earlier, systems treat each word as an atomic unit, meaning each word is just an index in a vocabulary. No relationship exists between words. For example, cat and there is dog. So cat has some index 105 and dog has index 876. Even though semantically they are very similar, the model has no way to know that. This leads to three major problems: no similar awareness, performance ceiling, data inefficiency. In no similarity awareness, cat and dog are unrelated. King and queen are unrelated. Even if we train n-gram models on trillion of words, they cannot capture deeper relationships. In data efficiency, tasks like speech recognition and translation need high quality label data, which is limited. So the key question becomes, how can we represent words such that meaning and similarity captured automatically? Now focus on distributed representation. It is our core concept. This leads to the idea of distributed representation. Instead of representing a word as a single index, we represent it as a vector of numbers. Like, for example, cat, we are going to represent it in a vector form. So there might be some kind of 010, there will be a vector. And dog, similarly, we can have 010, a single vector. These vectors can be close to each other according to their relationships, and they can be different. It means similarity is encoded as distance in vector space. In our vector space, the difference between 2 points is going to tell how much they are similar to each other. If they are very similar, they are going to be very close, and if they are far away, then they are not that much related. And we have important properties. Dense vectors, not sparse like one hot, and typically we have 50 to 300 dimension data, and it can learn automatically from data. So instead of manually defining relationships, the model learns them from context. Now let's focus on linear regularities in vector space. This is one of the most powerful discoveries in the paper. Not only do similar words cluster together, relationship become linear transformation in vector space. For example, king minus queen plus woman, it is going to be equal to queen. Like we have vector king and we have vector man and we have vector woman. So if we are going to minus vector man from vector king and we are going to add the vector woman, so it is going to result the vector queen. We are going to get the vector of queen. So now by removing man, it is going to show us that we are removing male, and by adding woman it is adding female, so result will be the woman. And it shows gender is a direction in a vector space. Similarly, from like if France, Paris, Germany, Berlin, then we are going to find out the logic behind this. And if we have running, ran, big, bigger, biggest, they are somewhere kind of similar words. So by this we can know by vector can define very much things. This is not we have trained manually, it emerges from the training. We train it and then we got it. Now let's focus on computational complexity. So the author defines training cost as training complexity is E multiplies T into Q. E means training epochs, T are the training words, and Q is the complexity per word. So E is going to show us how many training epochs we are using, and T is telling us the training words, and Q is the complexity of our model, and that is per word. Now here is the key. We cannot easily reduce E or T because we need more data. So the only thing we can optimize is Q, model complexity. And that's exactly our paper is doing, word2vec. So now let's focus on the previous models. What are they doing? That is NLLM and RNN. So before word2vec we had neural network language models, and their architecture is input previous words, and we have projection layer, and then we have hidden layer, and output will be probability over vocabulary. So the hidden layer introduces heavy computation. So there are lots of computation going on, and in this also the term h into v is going to dominate. If vocabulary equals to 1 million, the computation become very huge. Even with tricks like hierarchical softmax, it is not going to perform that much good. Now let's focus on RNN LM. So RNN improve by capturing sequence using hidden state memory, but still have hidden layer, and complexity is very high, and that is h into h plus h into v. So again it has limitation, expensive, and it is not that much scalable. So now let's move forward. So the core innovation is we have removed the hidden layer. So this slide is the heart of the paper. The authors observe most computational comes from the hidden layer. So they propose something radical. Remove the hidden layer entirely. At first this seems like we lose expressive power, but they argue if we simplify the model, we can train on much larger data, and experimentally they show more data plus simpler model is more powerful than complex model plus less data. So now let's focus on word2vec models, that is CBOW and skipgram. So SIBO is continuous bag of words, and our goal is to predict the current word using surrounding predict the current words using surrounding word. For example, wt minus 2, and if we have wt minus 1, wt plus 1, wt plus 2, and then it is going to predict the next word. Like if we have the previous words, we have a chain of sequence of words, then we are going to predict the next word in the chain sequence. So let's say the cat sat on the mat, then context is the sat, the sat on the, and we have target is cat. So now there are steps. Convert. Now we are going to convert each context word into a vector, average them, use that to predict target word. And here key design choices are no hidden layer, all vector share same matrix, order is ignored because we have bag of words. Why ignoring word works? Because local context still carries meaning. Like if we have mm, if we have totally ignored the order, it's fine because the local context also have some meaning, so we can rely on that. Now let's move forward. Now we'll see SIBO architecture and deep dive into it. So now Q equals to n into d plus d into log v. So compare this to an LLM, huge reduction. This is why SIBO trains in minutes instead of days. Now let's focus on skipgram. And the skipgram does the reverse. Given a word, predict its context. For example, we have input cat, and we are going to predict the sat on mat. So instead of averaging context, we learn how a word relates to its surrounding. Now here we have some important details. Window size C controls how many context word. Larger C, better semantic capture, but higher computation. Now distant word are sampled less because they are less related. And why skipgram is so powerful? It works very well for rare words because each occurrence generates multiple training signals. So now here we have the architecture. Now let's focus on differentiating between bag of words and skipgram. So SIBO is very fast and skipgram is very slower. SIBO averages the context, but skipgram predicts multiple output. And now we SIBO better for frequent words, but skipgram is better for semantic relationship. So in practice, use skipgram when accuracy matters, and we are going to use SIBO when speed is going to matter. Now let's see optimization techniques. So this is major trick, and the problem is softmax requires updating all vocabulary words. So if v equals to 1, so if vocabulary is 1 million, then it is going to be too slow. So there is one solution, only update few words. So for example, we have positive sample cat and negative samples are car, tree, phone. So we are going to only train cat with probability 1 and others as probability 0. So instead of OV, we get k equals to 5 minus 20. This means 100 minus 1000 times speed up. So it is going to be very good for us. Now let's move forward, and now let's see one more technique of optimization, that is hierarchical softmax. So vocabulary is stored as Huffman tree. In this we are going to store vocabulary as a Huffman tree. Instead of predicting among all words, we traverse a path in the tree. Frequent words, shorter path, and cost is going to reduce to log v. Very efficient for large vocabularies. Now training at scale. Now let's see this. They use dist belief, that is distributed system, 100 plus machines, async sgd, and result is going to be trained on 6 billion words in 2 days. Was very revolutionary at that time. Now let's see the syntactic analogy task. They evaluate using analogy questions. Like if we have biggest, big, small, then what it is going to predict the next? It should predict biggest, big, small, and something smallest, something like that, the more closer word. So this works because relationship are linear in a vector space, so it is going to find some vectors which is going to relate with this analogy. Now let's move forward and let's take some example. Like we have semantic France, then Paris, Germany, Berlin, and in syntactic it's run, running, big, bigger. So this it is going to test both grammar plus meaning, so we can do both things. Now let's move forward. So they are going to train these on somewhere around 6 billion words, 1 million vocabulary. So the key insight is training on more data is more powerful than more epochs. Now we have the results, and as the result shows, skipgram best semantic accuracy, SIBO best syntactic accuracy, and skipgram is somewhere around 65.6 total accuracy, and bird of wag SIBO is 63.7%. Also increasing dimension improve results, but after 300D dimension it is going to dimensioning returns. So now here we have all the data, how much they are accurate, and there is comparison between SIBO and skipgram. Now here is one case study. It is sentence completion task, skipgram plus RNN. It is going to give us the best performance, and shows embeddings are useful beyond simple similarity. Now there is visualization. Vectors capture relationship. Like if we have one word apple, then it is going to relate with us with iPhone, and we are using, it is not going to relate with, if the context behind is technology and products, then it is going to relate it with iPhone. And if there is context is fruit, then it is going to be apple with fruit. And similarly Google with Android. Now countries and capitals, France with Paris, Germany with Berlin, and now companies and OS, Google and Android. If there is some like food and their names, then Apple is going to relate with fruit, something like that. Science and culture, then here is we have Einstein with scientist, Picasso with painter. Now Let's move forward and let's see their applications, impact, and legacy. Now, the applications of Word2Vec. It is applicable on search, translation, QA systems, and there are lot of things uh, we are using. We are using it in machine translation, question answer, answering, named entity recognition. Now here we have seen how we we are at Word2Vec and how we evolved with the time. Now here are the conclusion of all of this paper. So here are the simpler model, scale better, meaning is encoded linearly, data is more important than architecture, Word2Vec is the foundation of the modern machine learning. Oh, sorry, natural language processing. Thank you.
Hello everyone, my name is Anurag Samata and I will be presenting the paper Enriching Word Vectors with Subword Information, published at TACL in 2017 by Peter Brzozowski, Eduard Grave, Armand Jolin and Thomas Nikolov, all from Facebook AI Research. This work will introduce what is popularly known as fast text word embeddings. This is a foundational paper in natural language processing. It builds on the famous word-to-vec framework and answers a very simple but important question: what if word embeddings could understand the internal structure of words, their root, prefixes and suffixes? By the end of this presentation, we will see how exactly they solve this, why it matters, and what results they achieved. So let's get started. Here is the here is our roadmap. We will cover 8 sections. First, the problem statement and motivation, why this paper was needed. Second, a recap of Word2Vec and its limitations. Third, the FastText model and its mathematics. Fourth, optimization and implementation details. Fifth, experimental setup and datasets. Sixth, the main results. Seventh, studies and analysis. And finally, a conclusion. So let's start with why word representations matter. So before we get into the details of paper, let's understand why representations matter at all. In modern NLP systems don't understand the text the way we do. So they need dense numeric vectors to compare meanings, compute similarities, and make predictions. The theoretical foundation for this is called the distribution hypothesis, proposed by Zelig Harris in 1954, which states that words used in similar contexts tend to have similar meanings. For example, dog and puppy both appear near words like bark, leash and fetch. Also, their vectors should be close. Good word embeddings improve nearly every downstream task: text classification, machine translation, information retrieval, sentiment analysis, and transfer learning. So getting word vectors right is critically important. So in every NLP system, use one-hot vectors. Early NLP systems use one-hot vectors, sparse binary vectors, where each word get a unique position and all other dimensions are zero. If your vocabulary has 10,000 words, then each word with is a 10,000 dimensional vectors with a single 1 to 9900 zeros. 9999 zeros. This problem, the problem these vectors encode no similarity. King and queen, for example, king and queen are just far apart as king and banana. There is no geometry, no semantic neighborhood. Dense embeddings to solve this. Words are mapped to compact vectors, for example 300 dimensions. where semantically similar words end up close to each other in vector space. This is fundamental shift that enabled modern NLP revolution. Word2Vec was one of the first and most influential model to learn these embeddings efficiently from raw text. So we'll see something little bit of Word2Vec. It was introduced by Mikolov in 2030 and has two architectures, CBOW and skipgram. CBOW takes the surrounding context word and predicts the center word. Given given the cat sat on the, so CBOW predicts mat for the next word. Skipgram does in reverse. Given the center word, it predicts the context word. For example, given mat, it would try to predict cat, sat, on, etc. So skipgram is generally more powerful, especially for infrequent words, because it trains the word vector directly by predicting many surrounding words. CBOW is faster but less precise for rare words. So the fast-text paper built directly on skipgram framework. Also, we can see architecture of word2vec. It has three it has three layers. One input layer which takes input to words and it averages out in projection layer, and then we will have an output word which is our predicted word. So we'll see a little bit of architecture of word2vec. In word2vec, each word is in the vocabulary has an embedding row, a vector learned during training. When word is the input, we simply look up its row. In CBOW, context word vectors are averaged to form a hidden representation. In skipgram, the center word vector is used directly. This hidden representation is then scored against output context vector using a dot product. The models learn by adjusting vectors so that true context words score higher than random words. Then full softmax over the entire vocabulary is computationally expensive. Imagine normalizing 10,000 words at every step. This is why word2vec approximate training using either negative sampling or hierarchical softmax, which we'll see shortly. So formally given a corpus of word W1, W2 and such that WT. The skipgram objective is to maximize the log likelihood of seeing context word given the center word. The scoring function is a sample dot product between the word vector UW and the context vector VC. The probability of context word is ideally computed as softmax, but as we said, this is expensive for large vocabularies. So instead, the problem is reframed as binary classification. In this context, word real or fake, this leads to the negative sampling objective, which we will detail in the fast-text slides. This architecture is elegant and fast, but it has one major blind spot, which is the fundamental motivation for fast text. So here are some limitations of word2vec. Word2vec assigns a completely independent vector to every word in the vocabulary. There is absolutely no parameter sharing between related words. Think about the words run, running, runner, and runs. These four words clearly share the same root and are semantically related, but in word2vec they each get their own word, own unrelated vector trained from scratch. Any signal learned for run does not help runner. So this creates two major failures. Rare words get poor representations. If running only appears 5 times in the training corpus, its vector is trained on 5 examples and is very noisy. Morphological rich languages suffer severely. Turkish, Finnish, Arabic, German, Czech, and Russian have enormous vocabularies due to inflection, declension, and compounding. Many valid forms appear very rarely or not at all in training data. So Word2Vec simply cannot handle all these gracefully. So we'll see motivation for fast text. So the core motivation is morphological rich languages have many inflected words form that must share structure. Rare and unseen words still contain character level patterns that carry meaning. Parameter sharing across related word forms allow a model to generalize better with less data. The insight is powerful. If you know the suffix ness signals a noun. Example kindness, happiness, darkness. You can use that signal across all such words rather than learning it separately for each one. This is the intuition behind subword modeling. So here is the central idea of fast text. Instead of assigning one vector per word, represent each word as a bag of character n-grams and define the word vector as sum of its n-gram vectors. So let's walk through the concrete example from the paper where the word where with n equals to 3 trigrams. First, add special boundary symbols. These angle brackets to represent start and end of the word. To mark the word boundary, so word becomes where. Then we extract all character trigrams. Example WH, WHE, HER, ERE, RE. We also include the whole word as a special token. That is where. This is important. The trigram HER different from the trigram H her inside where. So the boundary symbols ensure that model distinguish prefixes, suffixes from internal character sequences. The word vector for where is the sum of the vectors for all these n-grams. Each n-gram has its own learnable vector, and since n-grams are shared across words, the model naturally learns transferable subword patterns. So let's see the fast text architecture. So in step 1, each word is broken into characters n-grams of length 3 to 6. This is the paper's default range. Boundary symbols are added before decomposition and then hashing happens. The number of possible n-grams is used to keep memory bounded. Fasttext uses a hash function, especially FNB1A, to map each n-gram to one of the 2 million buckets. Multiple n-grams may map to the same bucket. This is called hash collisions, but in practice it introduces only minimal noise. Then, in step 3, the word vector is computed by summing the vectors of all n-gram buckets. This is the representation used for scoring. That is called aggregation. And then for scoring, the aggregated subword vector is then used exactly like word vector in skipgram, scored against context vector using a dot product and trained with negative sampling. The beauty of this design is that all words forms sharing character subsequence automatically share parameters. Learning from running improves runner because they share n-grams like run, un, and nni. So let's see some mathematical formulation. In standard skipgram, each word W has vector UW and scoring function between word W and context C is this. So in fast text, instead of UW being a single learned vector, it's constructed from n-gram vectors. So where GW is the set of all character n-grams of word W. including the whole word as a special token. ZZ is the vector associated with n-gram, so the scoring function becomes sigma of ZW dot product ZT transform dot VC. So this one change replacing the single word vector with sum of n-gram vectors is the heart of fast text. It enables parameter sharing, out of word vocabulary handling and morphological generalization all at once. At inference time, for an out of vocabulary word, a word never seen during training, we simply extract its n-gram, look up their hash bucket vectors, and sum them. We get a meaningful vector even for words the model has never seen before. This is a capability word2vec completely lacks. Okay, now let's talk about how fast text is trained efficiently. The objective uses negative sampling, the same approach as word2vec for every real word and context pair. The model also samples k-random negative context word that shouldn't be predicted. And here is the loss function. Minus log softmax s w comma c minus log then sigmoid function negative of s w comma ni, where this is the sigmoid function, sigma is the sigmoid function, swc is the score for the true context word, swni are the score for the k sampled negative words. This turns the expensive multi-class problem into k plus 1 simple binary classification. Is there is this a real context pair or not? The gradients are cheap to compute and the model trains efficiently. In the paper, k equals to 5 negative samples are sampled per positive pair, with probability portioned to the square root of the unigram frequency, a technique borrowed from word2vec that balances high frequency word dominance. So briefly, the other approximation option is the hierarchical softmax. Here, the vocabulary is arranged in a binary tree, often a Huffman coded tree where frequent words are at shallower depths. Computing the probability of a word requires traversing a path from root to leaf, which takes order of log v operations instead of order of v. While the paper primarily reports results using negative sampling, hierarchical softmax is also a valid option, especially when you need proper probability estimates. The paper's main experiments uses negative sampling as it's generally faster in practice. So a critical engineering in detail. The number of possible characters and grams across a large multi-number corpus can be astronomical. Storing separate word vectors for all of them is impractical. So fast text uses fnb 1a hash function to map n-grams into k equals to 2 million fixed buckets. For n-gram, so instead of storing one vector per unique n-gram string, you store exactly 2 million vectors and look them up by hash index. Hash collisions, where two different n-grams land in the same bucket, do occur but empirical impact is negligible. The hashing trick is what keeps the model's memory footprint manageable even for very large vocabularies. So for training, each word in the corpus decomposes into n-gram, sum their vectors to form UW, which is the word vector. Compute the loss against true and negative context word and backpropagate gradients to update the n-gram vectors ZZ. For inference, any word whether seen or unseen exact n-grams, sum their bucket vectors and use the result as word representation. No retraining needed. These unified rules make FastText both simple to implement and robust in practice. Now we'll see some implementation details and training speed. So the embedding dimension is 300 used in the paper, and context window is sampled uniformly from 1 to 5. Negative samples are 5 per positive pair. Negative subsampling threshold is 10 to the power minus 4 for high frequency word. It is a technique to downweight very common words like the and of. The and of. Step size Y naught is 0.05 with linear decay during training, and n-gram range is 3 to 6 characters. Regarding speed, on English data, FastText processes approximately 1,005,000 words per second per thread compared to 145,000 words per second per thread for the skipgram baseline. This is roughly a 1.5 times slowdown, which is very modest cost for all the added capability. The model is implemented in C++ and was open source on GitHub. So for dataset and languages, the authors evaluated on 9 languages from diverse language families covering different morphological profiles. They used Arabic, Czech, German, English, Spanish, French, Italian, Romanian, and Russian. And the training uses Wikipedia dumps in each language. The multilingual setup is essential. It lets the author demonstrate where subwords modeling helps the most, morphological rich languages, and where it helps less, simpler ones like English. So the first evaluation is word similarity, where models cosine similarity between word pairs is computed against human judgment scores using Spearman's rank correlations. Higher is the better. So here is the key results. German GUR 350 fast text scores 70 versus skipgram which scores 62 and CBOW 62. That is a significant jump. And English rare words fast text scores 47 versus 43 for both skipgram and CBOW. And Russian HJ fast text scores 66 where skipgram scores 60 and CBOW scores 59. So the pattern is very clear. Fast text wins decisively on rare and morphological complex words and matches baseline on common words. So this demonstrates that subword information is most valuable exactly when it's needed. And for analogy task test whether models capture relational structure, that is, for example, A is to B, that C is to D. Results are split into semantical analogies. Example: capital cities, gender pairs, and syntactical analogies. Example: verb tenses, nouns, plurals, and comparative forms. The syntactic results are striking. For Czech syntactic, 77.8% accuracy is with fast text, where skipgram gives only 52.8% accuracy. That is 25% point jump. And for German syntactic, 56.4% is given by fast text, where skipgram only scores 44.5%. So why such a big gain? Syntactic analogies test exactly kind of regular morphological transformations that characters n-gram capture. Verb endings, case suffix, and plural forms are all encoded in the n-grams. The fast text learn these patterns across many words simultaneously. For example, semantic analysis, fast text is competitive but doesn't always win. Sometimes the performance is slightly lower, especially in German. This makes sense. Semantic relations depend on co-occurrence pattern and context, not character structure. However, the syntactic wins are more than compensate overall. So the paper also compares fast text to methods that explicitly use morphological information. Method that require a morphological analyzer to segment words into stems and affixes before training. These includes long as recursive neural network for morphology, QATL's morpheme, Scorekits, Seabaugh Soicat, and Oak's morphological transformation, and Bothas and Blumson's log bilinear language model. FastText is competitive or superior to all of these. Despite being much simpler, it needs no external morphological analyzer, no pre-processing pipeline, and no language-specific rules. It discovers morphological structure implicitly from raw character sequence alone. This is a very significant result. An unsupervised learning agnostic method beats hand-engineered morphological approaches. So now we'll see effect of training and data size. One of the most practical important experiments test how fast text performs as training data size decreases. The authors train model on 1%, 2%, 5%, 10%, and 20% and 50% of the full Wikipedia data. The key finding is that fast text trained on 5% German Wikipedia outperforms Seabaugh trained on 100% of German Wikipedia. So you need 20 times less data to achieve the same quality on English rare words. Fast text with 1% of the data matches with Seabaugh on 100%. Why? Because fast text can generalize from the n-grams of seen words to unseen forms. Even if microbiologists never appeared, for example, microbiologists never appeared in training, its n-gram like microbiology were probably seen in many other words. Seabaugh, on the other hand, needs to see every word formed repeatedly to learn its vector. This has enormous practical implications for low resource languages, specialized domains, and situations where labeled or clean text is scarce. Now we'll see effect of n-gram range. This paper also studies how choice of minimum and maximum n-gram length affects performance. Results are reported for all combinations of min n and max n from 2 to 6. Key findings. The default choice of n from 3 to 6 is strong, stable settings across both English and German. Including long n-gram up to 6 is important, especially for German, because compound nouns requires longer character sequences to capture the relevant morphological units. Using 2 n-grams as the minimum does not help. They are too short to capture meaningful morphological structures. Diagrams like th or appears too many different contexts to be informative. For analogy tasks, longer n-grams help with semantic analogies. Specifically, for analogy tasks, longer n-grams help with semantic analogy specifically. The takeaway from 3 to 6 is robust defeat, but practitioners should tune based on their language and task. Beyond word similarity and analogy, the authors test whether fast text vector help language modeling. They initialize an LSTM language model with either random vectors, skip-gram vectors, or fast text vectors, and measure text perplexity and measures text perplexity. So the lower perplexity, better it is. Result across 5 languages. Czech, German, Spanish, French, Russian. Fast text vectors consistently reduce perplexity compared to both random initialization and skip-gram initialization. The most dramatic gains are in morphological rich languages. Czech improves by 8%, Russian by 13% over skip-gram initialization. For languages like Spanish and French, the gains are smaller, 2 to 3%, but still consistent. Now we'll see qualitative analysis. The paper includes insightful qualitative results. For nearest neighbor, technique for rare, technical, and complex word, fast text nearest neighbor are much more semantically coherent than skipgrams. For example, micromanaging has neighbors like micromanage and micromanaged in fast text, while skipgram retrieves unrelated words. By analyzing which n-grams contribute most to a word vector, the authors find that the most important n-grams often correspond to real morphemes. Linguistically, meaning subverts units. For example, German word Autofahr, which means car driver, has auto and fair as its most important n-grams. For out-of-word vocabulary words, fast text correctly identifies shared subword structure with known words. For instance, microcircuits share n-gram with both micro and circuit. Related known words as its out-of-order vector reflects this out-of-order vocabulary vector reflects this meaningful combination. These qualitative results give confidence that fast text is not just optimizing a metric but actually learning linguistically meaningful structure. Now let's talk about when to use fast text and what to be aware of. So where fast text excels? It excels in morphological rich languages and rare word heavy domains, medical text, legal text, technical documentation. Resource constraint deployment where we can't afford large contextual models. Noisy text with typos. Since character n-gram provide partial robustness. But what are its limitations? Static embeddings. Fast text gives one vector per word form regardless of context. That is, for example, the bank and the river bank get the same vector. For the word bank, character similarity is not equal to semantic similarity. Therapist and the rapist share n-grams but are semantically unrelated. Hash collisions. Minor noise from the hashing trick. Contextual models like BERT dramatically outperform fast text on tasks regarding sense disambiguations, but they cost 100 times more in computation. Now, for practical deployment tips, start from pretend fast text vector when available. Retrain on domain-specific data for specialized application and tune n-gram range and bucket size based on memory budget. For any word reproducing this work, document corpus preprocessing and tokenization decisions should keep in mind hyperparameters such as dimension, window size, negatives, n-gram range, bucket size, and should track out of vocabulary handling policy in all baselines. So for summary, fast text introduces a simple but powerful idea. Represent each word as bag of character n-grams and define word vectors as the sum of n-gram vectors. This single design decision gives three major benefits. Better rare words representation through parameter sharing across morphological related forms, out of vocabulary handling by composing n-gram vectors for any unseen word, morphological awareness by implicitly learning roots, prefixes, and suffixes without any external tools. The paper shows state-of-the-art results on word similarity and analogy tasks across 9 languages, outperforms specialized morphological models despite being simpler, and demonstrates remarkable data efficiency, needing 20 times less data to match word-to-vec in some settings. FastText became one of the most widely used NLP tools in the industry precisely because it delivered strong multilingual quality at practical deployment cost. It is a testament to the power of well-motivated simple architectural ideas executed rigorously. So last but not the least, thank you for your attention.
So, hello everyone. We have selected the paper Attention is All You Need from the pool 3. My teammates are Akash, Anurag and Subham, and I am Deependra. So first of all, we need to discuss what's the problem with the sequential model. Why we are going to transformer. So suppose we have a sentence like the cat sat on the mat, was hungry. Now I want to find what word will come after the word was. So in RNN, I need to calculate from starting. First of all, I will calculate the cat that sat on the mat in a sequence. First, I will convert this sentence, convert each word of the sentence in vector, then process x1. Initially hidden information is 0. For the second word, I have some previous information, some hidden information. Similarly for the third one, and in this way I will go process. I will make my process. So the limitation of the RNN and LSTM are no parallelization. I need to go from starting to the word was. After that, I can find hungry. Long-term dependencies. Long-term dependencies means I cannot work with previous 4 word, previous 5 words. I need to go from starting. So that's why the training is also slow. Now the transformer comes into picture. In the paper, Attention is All You Need in 2017. The main part of this transformer is self-attention mechanism. It works on self-attention mechanism and it does not require any recurrence or convolution. The main part of the transformer are encoder and decoder. So this is the basic structure of transformer which is given in the paper. In the basic paper, in the original paper, it contains encoder and decoder. This is only one layer and the architecture consists of 6 layers of encoder and 6 layers of decoder. Each layer contains multi-head attention and feed-forward network in encoder part, and in decoder part, mask attention, after that multi-head attention, after that feed-forward neural network. In the original paper, dimension of the model is taken 512, 6 layers and 8 attention head. Dimension of feed-forward neural network is taken 2048. After that, I will explain the decoder part. So let me explain the decoder part with the help of an example. Suppose I am taking a sentence like Ravi is reading NLU. So what's the meaning of this? Is our input part. We have input our sentence. This is our input. Now input embedding. Input embedding means each word will be converted in a vector, like 1, 2, 3. A space will also convert it something vector. Each word will convert it in some vector. Now it comes positional encoding. Why we need positional encoding? Since we have a unique vector for Ravi, unique vector for age, unique vector for reading, and unique vector for NLU. But model does not understand this sequence. To give the sequence, we need positional encoding. Like, so what method we use for positional encoding? I will explain this thing in some uh, after some slides. So let me erase this part now. This is only one layer part. We consist of 6 layers. So first of all, input and positional embedding, then add residual. This is after this positional encoding, a residual part will go, and we will have 3 input for multi-head attention. So what are those 3 input? The first one is query, key, and value. How to find these? Key, value, and query. So we have our source, like we have initial data, some data. From that data, like a paragraph or sentence, we have only one source. One source, not one sentence, collection of sentence, but one source. So from that one source, we convert that into position word embedding. After that, positional encoding. After that, we gave 3 input in the mask attention. So these are Q, K, and V. How to find this? We have X. Suppose the after encoding the vector is X, then we have matrix WQ for query, WK, and WV. These are parameterable, means these are learnable. We will learn as training proceed. So these are the information of Q, K, and V. How will we find these vectors? And the formal definition is attention is written here. After that, the term comes attention. Since we have same source for the data for Q, K, and V, but from this part, the model learned the context of the sentence. Which word should you can understand the context of the sentence. So that's why this is called self-attention. Since the source is single for Q, K, and V, still this attention part can understand the context of the sentence. That's why this is called self-attention. So how it works? The first step is we calculate Q and K. Since Q is collect, if we have processed a sentence, then Q, K, and V are matrix. So we will make dot product. After that, we scale this. We are scaling this thing because the dimension should not be too much large. The multiplication should not be too much large. Suppose one value is 1 and another value is 1 and too many big value. That's is not good thing. We cannot manage this with low calculation. So we make scaling here with the dimension, with the under root of dimension. After that, we apply softmax. After applying softmax, our this thing comes between 0 and 1. After this thing comes between 0 and 1. After that, with sum of V into we multiply with W. This whole thing is called attention. This is the figure of attention. Oh, sorry. So how multi-head attention comes? Since initially I explained that we have 6 layers, but we can have too many layers. That's why this is called multi-head attention. We give V, K, and Q after dot product attention. This box is showing the previous part. This whole part is shown here with this violet box H. After it, we concate all these, and a linear multi-head attention provides a linear. We can also say a vector. So we have multi-head attention. How we find this multi-head attention? We have head one, head two, head too many heads. This is the Q A means this is showing the attention part. One attention. We have too many attention. Call them attention one, attention two, like this. Then we concatenate this and multiply with WO. Sorry for the inconvenience. So now the question comes, which I have previously leave, that how to do positional encoding. So suppose I have a sentence, call the sentence as my name is Deependra Soni. Oh, what is happening? My name is Deependra Soni. So this is position 1, this is 2, this is 3, this is 4, this is 5. We use sign off for, let me do it for odd position first. So cos of 1 by 10,000 to the power 2i by dimension of model. Suppose we have some dimension. So this is the formula. And the solution is sinusoidal encoding. What is the benefit of using this encoding? This handle unseen length. Like we have too many sentences, a paragraph contains 1 million of sentence. If we use a normal encoding, this normal encoding may increase to millions, but this sinusoidal encoding put the embedding between 0 to 1, since sine function and cos function put their value between 0 to 1 or 0 or 1. So this is our positional encoding, injecting order into the model. Now position wise, after that part, positional encoding, we have multi-head attention. I explained the multi-head attention part previously. So after that multi-head attention part, we are coming from position wise FN. FFN. So what this FNN does? FNN and embedding. So embedding convert word into vector representation so the model can understand them. We also add positional encoding to preserve the order of word. After that, each word is passed through a feed-forward neural network that I have shown with the formula. This network has 2 layers, where the dimension is first increased and then reduced back. In simple terms, if I say attention capture relationship between words and the feed forward network process each word more deeply. And these are the output of this whole thing. Dimension which are taken in the original paper are input and output dimension of 512 and inner layers are 2048 for the FFN. So our encoder part is complete. Now we are in decoder part. There are 3 main parts, only 3 parts in decoder which are main. The first one is masked multi-head self-attention, cross attention, and then position wise feed forward neural network. So this is same cross attention encoder decoder. architecture. This is also same. The main difference is in masked multi-head attention. So suppose our model is trained. Okay, so first let me explain the whole. So while inference or training, our input go from there, then we do output embedding, then we do positional encoding. I have already explained all these parts. Then we have mask attention, multi-head attention. What this term do? This term do, like our query depends on the first query depends on only first word. So this thing mm, does not allow to see the other or future terms. In simple words, it only allows the model to see previous word, not the future word. That's called masked multi-head attention. This attention is applied in each sequence, each head. That's why multi-head. After that, cross attention encoder, decoder, encoder attention. So our multi-head attention go from there, and we found key and value from the encoder part. In the initial model, this both was uh, जुड़े हुए थे, added, but I cut from middle and separate both encoder and decoder. That's why. So key and value pair we got from there, and output from and output of mask attention layer there. After that, this part and feed forward neural network part is same as previous. And this is the summary of all. You can see this. Now let me explain the multi-head mask attention with an example. Suppose we want to find what will come after the word way. What will come after the word way? Okay. What will come here? Here. Okay. So we need to do it from initially. E is encoding and P is position vector. E is encoding and P is positional vector. We apply KW and found E. This is key 1. This is query 1. This is query 2. We input where. After that, we input there. So if I say this this query depends on only first key, this thing only depends on first and second key 2. Like in this image you can see first only depend on first one, second only depends on first and second. Similarly, ith depend on ith term, so we need not to see all these terms. So what can we do? We put minus infinity all these. After softmax, these value becomes 0. These value becomes 0. That means we have applied a masked here. This is a procedure of masked multi-head attention, right? Minus infinity. After that, we will apply softmax and go and got the 0 value here. So this was the brief introduction of the model which was introduced in the paper. Attention is all you need. Now, if we compare all these previous model and our self attention, then now we are comparing self attention worked and complexity analysis. So layer type, complexity of layer, sequential and maximum path length. So this one, so you can see all these things. In all the things in parallelization, self-attention win. Self-attention recurrent RNN, convolution, and self-attention restricted. Which one is going to be winner? In parallelization, winner is self-attention because self-attention connects all position in order one sequential operation. In long-range dependency, also self-attention win. But in computational cost, self-attention took some more computation time. So if we increase some computational cost and we are getting profit in both these, so what's the harm of not using this? No, sorry, what's the harm of using this? Now the model was done, model preparation is done. It's time to training setup. According to the self attention is all you need original paper. These are the training data, hardware and schedule. Optimizer is used as Adam and regularization used as dropout, label smoothing, and all these things. So when it compared to machine translation, we saw that basenet is bytenet is going getting only 23.8. After that, all these we apply the model and found the transformer, the big one, as highest, something 28.4, the highest. When we were converting from English to German, from English to French, when we was converting, we check all these models. Sorry, not we, the original paper maker. Check all these paper and found the bigger base transformer. This one is getting 41.8% accuracy. That's a wonderful thing. That's a very good thing. Now training efficiency and the cost advantage. The measurement is BLEU. BLEU means the transformer base model achieve higher base accuracy, higher BLEU than all other prior published model and ensembles, while requiring only approx 7 into less computation, 7 times less computation than competing single models like GNMT and plus RL, all these. So this is taking more than 7 times, approx 7 times more time, and the blue score is 28.4, more than all. Blue is a type of measurement, like I have described somewhere about blue, but I am not seeing. Okay, I have described here what is blue. Now, after all the setup, we checked our transformer is performing very well. The generalization, English constituency parsing. Does the transformer generalize beyond translation? So all the summary of all these experiment is without task specific tuning, the transformer generalize well to a structurally different NLP task. This is the very good thing. Now, if we compare the transformer versus RNN, so this is a very good comparison. Let's see. Parallelization transformer, full parallel training. It is using long range dependency is only order 1. Memory of content, direct access to all positions. Training speed much faster on GPU. Inference, compute all position even for one token. Very long sentence. Order of n square. Memory for attention. But this is something like this. And all these things, our transformer is winning. But data efficiency, we need more large data to sign, but RNN can work in a smaller data. Now these all are the conclusions. The transformer is the first sequence to sequence model based entire on attention. It replaces CNN, RNN, multi-head attention, achieve significant faster training compared to RNN and CNN network. Results are shown on the English to German and English to French task translation task. Demonstration that attention alone is powerful enough for sequence modeling. And these all are the results, conclusions. These are the reference. So this was the explanation by me, and thank you.
Today I am going to present a very important paper named BERT, which is known as Pre-Training of Deep Bidirectional Transformation, which is proposed by Google in 2019. This paper is considered a milestone in natural language processing because it is changed how machine understand languages. How many modern AI systems today are built on ideas introduced by BERT. So in this presentation, I will explain you the motivation behind BERT, how it works, its architecture, its training techniques, and its performance on real tasks. So we will move to its motivation. Basically, human language is highly context dependent. A single word can have multiple meanings depending on the sentences. So, for example, he sat near the blank. Here, we suppose the word riverbank. This is not clearly mentioned, and traditional models assign fixed meaning to words, which is a major limitations. Also, many NLP tasks like question answering, translations, sentimental analysis require understanding the entire sentence context, not just individual words. So the key question is, how can we build a model that understand language like human? So the major problem is limited context understanding. So before BERT models have had major limitations. So they are most models are unidirectional, meaning they are reading text either left to right or right to left, as GPT says. This causes problem because words cannot use future context, and sentence meaning is incomplete. And the another issue is different tasks require different meaning and different architectures. This increased complexity and engineering efforts. So overall, existing models were not suitable for deep language understanding. We have different model for different tasks, but we require different architecture for that. And the performance is the also the major issue for the models on different tasks or complex tasks. So BERT is the solution. BERT solve these problems using a new approach. It is a breakthrough. Here BERT stand for bidirectional encoder representations for transformers. The key idea is it reads text both left to right and right to left, and it is based on transformer encoder architecture, which should be pre-trained on large scale unlabeled data, and then we perform fine tuning for specific tasks. Unlike previous model, it considered full sentence context at once. So now we discuss transformer encoder architecture. The key tasks of BERT. The major task is uh, basically to mask language model MLM and the next sentence prediction NSP. Both task has been used for pre-training in the BERT. And BERT introduced the innovations. BERT achieved state-of-the-art results, outperform previous models on multiple tasks. Now we will discuss about BERT architecture overview. BERT basically uses transformer encoder. The key component is self-attention. You can see in the diagram. The key property is bidirectional self-attention, which is all to all. For example, the red fox jumps. Here, the fox can be jumped by directly, and fox give you attention weight. So each word generate representation by attending to the entire context simultaneously. So self attention helps resolve such relationship. It gives some advantages like capture long distance dependencies, process word in parallel, and improves context understanding. But architectures based on encoder stack, which has different layers. So now we will we in this model the size is different, and the basics of transformer, it uses self attention, and each word attend all word other. Advantages is parallel processing and long range dependencies. As we the model size is uh, basically BERT come in two versions. So which is first is BERT base and the second one is BERT large. BERT base contains 12 layer and 110 million parameters. And the another side, BERT large contain 24 layers and 340 million parameters. So larger model learns better representation but require more computation power. So there is trade-off. Here is the each word in is converted into a vector using three components, which is token embedding, segment embedding, and position embedding. You can see in the diagram which shown as below. So token embedding means word label representation, word meaning, or word sense, and the second one is segment embedding, which means segment identity or sentence identity, and the last one is a position embedding. It means the order of the words. It maintains word order. So final input contains token, segment, and the position. The final input is here using all of three. Here we see the special tokens which is used in BERT, which enables task flexibility. First one is classification tokens, which is known as CLS, and the second one is separate tokens, which is known as SEP. For example, CLS questions SEP passage SEP, which means the unified format for BERT to handle single sentence task and sentence pair task. So instead of designing different models, BERT use one unified architecture. So general input structure is CLS sentence A and SEP sentence B and SEP. Case 1 single sentence task used in sentimental analysis and test classification. For example, CLS classification task, the movie is amazing, and end with SEP. And the case 2 is sentence pair task used in question answering and natural language interface inference. So CLS, what is AI? And SEP, AI is artificial intelligence, is SEP. So end with SEP. So BERT convert all tasks into a single unified input format. So now we come with pre-training, which is the main part of BERT. It learns from unlabeled data. Pre-training is the most important phase. Here, BERT learns from unlabeled data like books plus Wikipedia as it is given. It learns grammar, it learns context, and understand the language patterns. This knowledge is later used for different tasks. Here, two core training objectives in pre-training, which is masked language model (MLM), and the second one is next sentence prediction (NSP). Now we discuss masked language model. Language model is the core innovation. Here, BERT randomly hides 15% of word and predicts them. To predict the word, the model use both left and right context. And unlike GPT, which uses only past words, this gives BERT a huge advantage. Also, making is done carefully, and it avoids limitations of left to right models. So MLM forces the model to understand the entire sentence, not just memorize the patterns. This prevents overfitting and improves robustness of the model. The strategy of the word, it is here is three making masking cases. First one is when we replace the with a mask, like for example, dog is cute, then dog is mask. Here mask is predictable word. When 10% with random words, that dog is cute, then dog is apple, then apple is just random word, and 10% then keep unchanged, like here is no change. So it has three basically masking case. So it predict original word using context from both sides, left to right and right to left. The loss function is use cross entropy. This makes strategy prevents the model from overfitting to the mask token. Mask long language modeling is effective and predicts mask words using left plus right context. So basically, MLM enables BERT to understand meaning, not just predict sequence. Here, the next one is next sentence prediction (NSP). It learns sentence relationship, and NSP predict helps BERT understanding relation between sentence. The model is giving two sentences, 50% correct and 50% random. Suppose we have a task, predict if sentence B follows sentence A. Then this is important because many tasks involves multiple sentences. For you can see sentence 1 is the dog is barking. Sentence 2 is it wants to play. Then experiment shows removing NSP reduce performance significantly. So NSP trains BERT to capture inter-sentence coherence, which is not learned by standard language model. Why NSP is important? The major question, the major issue is कि in the standard language models, because it learns only within sentence relationship and cannot capture sentence order and logical flow between the sentence. But in case of NSP, it trains model to predict if sentence B follows sentence A and learns sentence coherence, sentence continuity, as well cross sentence meaning, which improves reasonability, reasoning ability, multi-sentencing, understanding, context-aware predictions. So, which is the major part of pre-training pipeline. Now we discuss pre-training pipeline. Training involves basically 4 steps. First one is input preparation. The second one is apply training mask. Third one is model training, and then output. BERT is trained on basically 3.3 billion words. It training required high computation. You can see high computation, TPUs, several days computation time, but the result is very powerful general purpose model. So here in the data scale you can see data used for book corpus around 8 million words, and the English Wikipedia 2.5 billion words. These database, why we use these database? Because it provides long continuous task, rich sentence relationship, real world language pattern. So basically the designing choice, we have to use large data for pre-training data, because for better contextual learning it is very essential. The configuration and efficiency, the training setup is basically 26 sequences batch size, and training step is 1 million, and total data is 3.3 billion, as we said. Optimization details, we use Adam optimizer, and the learning rate is 1e4. The drop rate is very low, which is 0.1, and the activation is GELU. So now we discuss the next part, which is fine tuning. When the processing done on pre-trained data, the next step is fine tuning. After pre-training, BERT is fine tuned. In this process, we add output layer and trained on task specific data. The main advantage of the fine tuning is it is fast and require less data, and for the same model for all tasks. It used for the same model for all tasks. So this is also called as transfer learning. Yeah, fine tuning basically second phase, and it start with pre-trained BERT model, and as add some task specific output layer. You can see different output layer, and it update all parameter end to end learning. We have basically three type of tasks in BERT. First one is a sentence level task, the second one is sentence pair task, and third one is token level task. In sentence level, it predicts output the entire sentence. For example, this movie is amazing, which means it is positive side, and when it is the movie is not amazing, then it may be natural or negative side. And the second one of task is sentence pair task. In this, it understands relationship between two sentences, like question answering, paraphrase, phrase redaction, check when we wants to check the meaning of two different sentences. And the third one is token level task, which is it predict output for each word, at each and single word. Like Delhi is India, then Delhi, what is Delhi? Delhi is location. India, what India is location, and is an in, it is verb or super verb. Fine tuning usefulness in the word is it contains minimal architecture changes. Only when we only add a simple output layer, then it works, and it requires efficient training because it is fast and lightweight. So because for example, squad model trained in 30 minutes only, so it provide end-to-end learning. The entire model is updated encoder plus output layer, and learns task specifically pattern effectively. So transfer learning advantage we have. So it reduce training time and computational cost overseas reuse. So now we will go in benchmarks. When we use BERT, then we have how can we evaluate the BERT. So we have different benchmarks in which GLU is best one. It is GLU is a benchmark which stands for General Language Understanding Evaluation. Basically, BERT achieved in this task, in this benchmark, 80.5. This shows strong generalization ability. Basically, GLU General Language Understanding Evaluation benchmarks provide generalization ability. It measures language understanding, reasoning ability, and generalization. So basically, two type of tasks is measured in GLUE. First one is single sentence task, and the second one is sentence pair task. Basically, GLUE test whether a model can generalize across multiple NLP tasks using one model, not just specifically performance. It's focus on different NLP tasks, not as just a specific task. So the performance, BERT performance, it contain 80.5, and improvement is plus 7.5 points, which is far more for over previous state of the arts. And when we compare with previous model, the OpenAI GPT provides 72.8, BERT base 79.6, but large provide 80.5. It is the table, GLUE benchmark table, and the test results. The second benchmark is squared task. It provide question answering task ability, and basically BERT predicts in this task, in this benchmark, BERT predicts start and end position of the answer. You can see start and end position of the answer. For example, where does he live? Then and he lives in Delhi. Then he understand the question ability and provide the answer by using passes. The answer is Delhi. So BERT convert question answering into a token level classification problem, which is the major task evaluated by squared. And the squared, when we tell about BERT performance on squared benchmark, then it is nearly 90.9 for BERT large in single mode, and 93.2 F1 score for BERT large in sample. So basically, BERT's success in squared demonstrate its strength in token level understanding and span prediction. Here, the another benchmark, which is the upgraded version of squared benchmark, which is it is the extension of squared V1.1 that includes questions that do not have answer in the passage. In this evaluation technique, it don't contain the answers from the passage. It takes what is the summary which provide you the answer. So the challenge is model must find correct answer, span, or decide no answer exists. There is two type of solutions. But how BERT use how BERT solve this? It uses special tokens CLS to present like no answer. It compares best answer span score versus CLS score, and if CLS score is more than answer span, then predict no answer, otherwise provide the answer. And the performance for BERT large model F1 score is 83.1, but cannot only find answers but also detect when no answer exists. And the another benchmark is SWAG, which stands for situation with adversarial generalization. It chooses most plausible sentence continuation. SWAG test common sense reasoning, the basic thing, common sense. The model select the most logical sentence continuation, and it shows but understand real words situations. For example, the context is she opened the door and saw. Then sawing something, some person or some pet or something. So for options A, a cat sitting outside. B, she was running yesterday. It is totally not match for this. So it is not she was running. It's the past case. But here saw is a different entity. The sky is blue. The sky is blue. She, it can be logical. Number are increasing. What number are increasing? There is no words. So the most logical sentence, the score will be the option A will be high. So the answer is a cat sitting outside. And the when we tell about performance, which bird stand at large accuracy, which is 86.3 percentage around. So bird can perform not only language task but also logical and common sense reasoning. The ablation studies, which is like when we remove NSP and bidirectional reduces performance, then what will be the situation? And ablation study is what makes BERT effective. Like techniques, it provides the techniques to test importance of components. If we remove one part, like I said, like if we remove NSP, then what will be the solution? And removing one part and observing a performance change. So, like it is the fine tuning results after no NSP. So you can see the observation, the major observation by ablation studies, by removing NSP, we can see the decreasing performance on MNLI, QNLI squared. You can see no NSP, the performance is downgraded, which is around 90, but here is 83.9 something. So it is much worse performance and cannot use for future task when we remove NSP. Next step, prediction. And the important finding is bidirectional training, MLM, and significantly better than unidirectional models. The conclusion is BERT success comes from combination of bidirectional learning plus sentence level training. So it proves that both MLM and NSP are essential for BERT success. And now the comparison, which is the main thing which provide the model success. So when we compare BERT model to other, the for different layers, like BERT base for 12 layers its parameter, but when we use large BERT base for large parameters, large data, the performance is better. So consistency improvement in accuracy. So larger model learns richer representation and capture complex patterns and improves observed across MLI and SS2 SST2 benchmarks. The another thing is the important insight, which is even with a small data set, the larger model performs better because knowledge comes from pre-training and then fine-tuning. So scaling model size improves performance when combined with large scale pre-training. Now we compare with different models like GPT, ELMO, and the key comparison is when we on the feature of architecture transformer. The GPT use decoder and ELMO use BLSTM, by LSTM, and BERT using transformer encoder. And for context direction, it use left to right. It use shallow bidirectional, but shallow. It use deep bidirectional. You can go for left to right and right to left in deep manner. The contextual understanding, which is main thing, is it is GPT for GPT it is limited, and for Elmo it is moderate, and for BERT it is very strong. And the key difference is GPT is unidirectional, so cannot use for future context. Elmo it combines left and right models separately and not deeply integrated. The major thing. But for BERT, it is fully bidirectional at every layer, which learns deeper contextual representation. So BERT combines deep bidirectional context plus effective pre-training, which making it superior to earlier models. Now we perform the comparisons, and now we will discuss the advantages of using to the word. First one is deep contextual understanding, because it is used bidirectional learning, as we as we see earlier, and it is high performance across all tasks. You can see in different benchmarks like Glue, Squad, and Swag. It is unified architecture. The same model works for classification, question answering, NER, and the only output layer changes for different tasks, not the entire model. And the effective transfer learning is the main thing for of the word, because when is doing pre-trained, it use reuse many tasks, and it reduce need of large labeled data set, because we cannot gather large amount of data, because it also has some headache. And the BERT combines strong language understanding plus flexibility plus efficiency, which making it powerful for general purpose NLP models. And now we see the negative part of BERT, which is limitations. It is where it is high computational cost, because it requires more powerful GPUs and TPUs for pre-training tasks, and it provides low inference, because bidirectional attention is computationally expensive, and we have no idea about real-time applications and how it works. We have no idea, and it is not designed for text generation. So for it uses encoder only architecture, and it cannot naturally generate long text sequences, so it is another issue. And it is less suitable for users than GPT for generalization tasks. And pre-training cost is also higher, so competition cost is issue. So but achieves high performance at the cost of efficiency, scalability, and deployment challenges. And now we end the whole paper with conclusion and impact of BERT in real life. Basically, in real world, search engines like Google search and chatbots and virtual assistants can use BERT, and question answering system and test classification is very really good for models. And the impact on NLPs, BERT achieved state of the art results on multiple benchmarks, which are because we have already discussed about it, and it became the foundation of modern NLP models, and it inspired models like Robert, Distilbert, and Albert, which is in future work. The major contribution in the BERT is first one is MLM, mask language models, and the second one is next sentence prediction. Then we go for fine tuning, where different layers works. So it provide a unified architecture for multiple NLP tasks. So using deep bidirectional learning, it can work both left to right and right to left. It can understand the logical reasoning of the sentences, words, and the context. So thank you.